So now, after we have discussed about the various characteristics of detectors, the next topic that I would like to talk about is simplified detector model. Okay, now you must remember that the net result of radiation interaction in a wide category of detectors. What is the net result? Radiation interaction. The net result is appearance of some amount of electric charge within the inside the detector active volume. Okay, thus আমাদের এই যে simplified detector model হবে, what will it does? It will thus assume that a charge Q appears within the detector at time t is equal to 0, resulting from the interaction of a single particle or quantum of radiation. Okay, next, so this is the first part, the appearance of charge. What is the next part? The next part is, you see, so next part is the collection. Okay, the charge Q, it must be collected to form basic electrical signal. Now you see, typically this collection of charge is accomplished through the imposition of an electric field within the detector. Okay, this is why we need some sort of force field. Come on, the charge has to travel, and then only after collecting the charge and analyzing the resulting pulse, we will be able to tell about the properties of the incoming radiation, right? So who will tell the charge that you go to that terminal, get yourself collected? When you go to a metro station, you buy the ticket, go to a particular counter, and after that you go to the particular train's channel, say yellow line, blue line, red line, something like that. So here the charge, if it is positive charge, if it is negative charge, it has to go to a particular terminal. So who will tell that charge to go? Of course, electric field. Okay, so the collection of charge is accomplished through the imposition of electric field E, right, within the detector, and this will cause the positive and negative charges which are created as a result of the radiation to flow in opposite directions. Now note that the time required to fully collect the charge, it varies greatly from one detector to another. So you will have to wait for that time, because until the charge has been collected, we will never be able to analyze, right? For example, you see, in ion chambers, the collection time in ion chambers, say for example, ion chambers, this collection time, it can be order of a few microseconds, milliseconds, even worse, milliseconds. Whereas in semiconductor detectors, here the same collection time, do you know how much it is? You will be amazed to know it is of the order of nanosecond. Okay, now these times, they reflect both the mobility of the charge carriers within the detector active volume and also the average distance that must be traveled before arrival at the collection electrodes. Okay, so now let us start to talk about how to model a prototype detector. Okay, so let's talk about modeling of a prototype detector. Whose response to a single particle or quanta of radiation will be basically what? Basically a current flow for a time equal to the charge collection time. Okay, now let me show you. So basically just a second. Okay, now this is the collection time TC, and so we will have okay, so this is equal to the total charge Q. Fine. So what I have just shown you, I have given you an example for the time dependence the detector current might assume, and this TC is the charge collection time. Okay, now what is this? So basically the time integral over the duration of the current, what will it be equal to? Just the total charge generated as a result of the interaction of the radiation with the detector. Okay, so this is my detector. As a result of this interaction inside the detector, this charge was created, and this is the response. Okay, now note that in any real situation, not just one quanta, not just one quanta, this is real world, but in the real world there will be many quanta. Okay, so what will happen? And they will interact over a period of time. Now if the irradiation rate is high, that means a large number of gamma rays are getting interacted in the detector, then what will happen? What will happen is that situations will arise where the current is flowing in the detector from more than just one type of interaction at a given time. And let us say, for example, let me assume that the rate is low enough so that each individual interaction gives rise to a current that is distinguishable from all others. The magnitude and direction of each current pulse may vary depending on the type of interaction. Okay, so what I am saying is, this is, say, a gamma ray of energy E1. What about when a gamma ray of energy E2 interacts, it will have a more detector volume and its response will be not like this, it will be something different. Okay, let me give you an example. So in reality what we will have is something like this. Okay, so basically the magnitude and duration of each current pulse, of course they will vary depending on the type of interaction, and here I have shown you the instantaneous current flowing in the detector as a result of one such interaction. Note that because the arrival of radiation quanta is a random process, so which is governed by what? Poisson statistics. So the time interval between the successive current pulses are also this one, they are also randomly distributed. Okay, suppose one gamma ray interacts with the detector and that gamma ray has higher energy. This means the charge that will be created as a result of the losing of the gamma ray. Suppose the gamma ray loses all its energy as a result of the interaction in the detector volume, active volume, then the charge will obviously be higher, right? The charge deposited, and here as a result of this you can see the current is much higher in this particular case. So this just tells you about the interaction, that this interaction has deposited a large amount of charge compared to other two interactions, and this interaction has occurred later, this one has occurred before. So if this is, say, this is a result, this is signal 1, this is signal 2, this is signal 3, then in the signal 3 the information that we are getting is that the particle has deposited more charge, and this means that probably its energy is much higher than that created by these two signals. Okay, ডিটেক্টরের ভেতরে চার্জের জেনারেশন কিভাবে হয় তুমি বলো। আমি যদি গামারে ইন্টারঅ্যাকশনের কথা ভাবি, গামারে এসে ইন্টারঅ্যাক্ট করলো, কিভাবে ইন্টারঅ্যাক্ট করতে পারে? ফটো ইলেকট্রিক এফেক্ট, কম্পটন স্ক্যাটারিং, পেয়ার প্রোডাকশন, প্রত্যেকবার। হ্যাঁ, এবার দেখো প্রত্যেকবার কি হবে, সামথিং উইল বি ক্রিয়েটেড, সে স্ক্যাটার্ড গ্যামা রে ইজ ক্রিয়েটেড। ওকে, Compton scattering, say for example, that scattered gamma ray, there is a possibility that ওই scattered gamma ray is again interact with the detector volume and it is completely absorbed as a result of photoelectric effect. Okay, so say for example, again আমি ছবি আঁকছি, দেখো gamma ray এসে পড়লো, say 700 keV gamma ray, 300 keV is absorbed, 400 keV scatters. This is again absorbed here completely by photoelectric effect. The first interaction is Compton scattering, next interaction is photoelectric effect. So what is happening is overall the entire energy is being absorbed, right? And so we will get an electrical signal corresponding to this 700 keV gamma ray. Okay then. Okay, so let me now talk about the important modes of detector operation. So what are the important modes of detector operation? Now I will talk about two very important modes here. One is pulse mode and another is current mode. Therefore, what happens in the pulse mode of operation, basically the measurement instrumentation, it is designed to record each individual quanta of radiation that interacts in the detector, and here the time integral of each burst of current, or basically the total charge, is recorded, since the energy deposited in the detector is directly related to Q. Now all detectors used to measure the energy of individual radiation quanta must be operated in pulse mode, and this basically applications of pulse mode, they correspond to radiation spectroscopy, and we will talk about this later on as well. Okay, sometimes what is done in a much simpler approach we can also do, and that is all pulses above a certain level threshold are registered from the detector regardless of the value of Q. Sometimes this is also done, and this approach is known as pulse counting. So above a certain threshold we just calculate, we just measure whatever is there. Certain threshold is important in this case. So this is pulse counting. I will also talk about this later on. Now, what happens when the event rate is very high? In this case, you see, the pulse mode of operation, it becomes impractical or probably impossible. Why? Because the time between the adjacent events, say between the adjacent events, one event, another event, if the time gap between them, it becomes too short to carry out an adequate analysis or the current pulses from successive events, then what will happen? They will overlap in time. In that case, then we will have to revert to alternative measurement techniques. Okay. Now, let me talk about the current mode in details. Now, if this is a detector, then what we have here, basically, so yes, here. Yes, so what I am showing you is basically current measuring device which is connected across the output terminals of the radiation detector. This is our radiation detector, RD. Now, if we assume that the measuring device has a fixed response time, then the recorded signal from a sequence of events will be time dependent current. What will it be? So let us assume that the response time is capital T. Okay, it is fixed. Then the time dependent current as a result of the interaction will be given by Now, to explain this, I will just use the previous drawing that I have drawn before. Let me again redraw this here, the previous case. So you remember this drawing. This is the previous sort of thing. Okay, so this is the current axis, this is the time axis, and this is the, what I am saying, the average current. Okay, this is this thing, average current. Now because the response time is typically long compared to the average time between the individual current pulses from the detector, the effect is to average out many of the fluctuations in the intervals between the individual radiation interactions and to record an average current that depends on the product of the interaction rate and the average charge per interaction. In the current mode, this time average of the individual current pulse bursts basically serves as the basic signal that is recorded. Okay, I will talk about pulse mode just a minute, but let me first talk about how this mode is done. This is the different approach, current mode. So you see, at any instant of time, what will happen? There is a statistical uncertainty in this signal due to the random fluctuations in the arrival time of the event. This is so the integration time t is quite analogous to the measurement time, right? Thus what will happen is that the choice of large t will minimize statistical fluctuations in the signal, but it will also show the response of rapid changes in the rate or nature of the radiation interactions. Now the average current is given by the product of the event rate and the average charge produced per event. What are these things? Let me write it down. Here R is the event rate. And what is Q? Charge collected, of course. So it is given by EQW, or basically charge produced per event. Here E is basically the average energy deposited per event, and W is the average energy required to produce a unit charge pair. Okay, and the value of E, this Q is basically E. Q is basically E here, which is just 1.6 10 to the power minus 19 coulomb. Okay, now so here, now see what happens. You see, for steady state irradiations of the detector, this average current can also be rewritten as the sum of constant current I0 plus a time dependent fluctuation component. Let me show. This is I0 okay, so this is my time axis, and so what I am saying is that for steady state irradiation, this average current I will write it as a sum of constant current I0 plus, say, what is this? This is basically sigma I. This one. So this is basically the fluctuating component. Okay, so see what is happening. What is basically happening is we are just mapping out. So previously we have such type of events coming in the detector. Now in this current mode of operation, instead of recording them, we are just noting the average current along with the fluctuations. So we are just having these two things here. They are representing the entire signal. Okay. Note that this sigma IT is random, time dependent variable that occurs as a consequence. Why does it occur? Come on, this is consequence of random nature of radiation, because the average time between them is random because of the random nature of radiation events within the detector. Okay. Any questions till now? Now, a statistical measure of this random component is the variance or the mean square value, which is defined as the time average of the square of difference between the fluctuating current I and the average current I0. Let me write it down. We are just basically characterizing the signal, how we can observe the signal, different ways of observing the signal, analyzing it. We are just doing that, and the present approach is known as the current mode. Okay. Here the standard deviation will just follow as usual. Now, if you will remember from Poisson statistics that the standard deviation in the number of recorded events n over a given period is expected to be just root n. Therefore, the standard deviation in the number of events occurring at rate r in an effective time, measurement time t, is simply r into t. Now, if each pulse contributes the same charge, then the fractional standard deviation in the measured, so fractional standard deviation in measured signal due to random fluctuations in pulse arrival time is given by this value, this ratio, and this is just 1 over R into T. So here this quantity is the time average of the standard deviation in the measured current, and T is the response time of the picoammeter, and I0 is the average current reading. Okay, here average current reading on the meter. This result is very important in estimating the uncertainty associated with a given current mode measurement. Okay, it is important to note that here in this derivation, the charge produced in each event Q is assumed to be constant. This is important. Here we have assumed that charge Q is constant. In each event. So this results account for only the random fluctuations in pulse arrival time, but not for fluctuations in pulse amplitude. Okay. Sometimes it does happen that the second source of variance, which is the fluctuation in pulse amplitude, that also happens. Anyway, we will talk about it later on. Now, any questions till now? Now, so if there are no more questions, so we will start with the second mode of operation, which is the pulse mode of operation. Now, you see the nature of the signal pulse produced from a single event depends on the input characteristics of the circuit to which the detector is connected, and this is usually a preamplifier. Let me draw an equivalent circuit. So this is our radiation detector. You already know what these are, right? Capacitance and resistor. Okay. Now, what is this R? R is basically the input resistance of the circuit, and C represents the equivalent capacitance of both the detector itself and the measuring circuit. Okay, this is radiation detector. So R is input resistance of circuit and C is equivalent capacitance of detector plus measuring circuit. Say for example, if a preamplifier is attached to the detector, then R is the input resistance and C is the sum capacitance of the detector, the cable used to connect the detector to the preamplifier, and also the input capacitance of the preamplifier itself. Now you see what happens in most cases. The time dependent voltage here Vt across the load resistance is the fundamental signal voltage on which the pulse mode of operation is based. Now, two separate extremes of operation, we will talk about them. They can be identified, and this depend on the relative value of the time constant of the measuring circuit. Now, what is the time constant? You see, from simple analysis you can say the time constant is just the product of R and C. So let me talk about these two extremes of operation. So the first one is small time constant, small RC. Okay. Now, in this extreme, the time constant of the external circuit is kept small, okay, compared with the charge collection time. Now, on your screen here, this is the assumed current output, okay, this one. This is the current output from the hypothetical detector. This we started with. And this is the case, this first case here, the small RC case. So the signal voltage, you can see the shape when we consider a small time constant load circuit. Now, as I was saying, in this extreme case, the time constant of the circuit, external circuit, is really kept small compared with the charge collection time, so that the current flowing through the load resistance R is essentially equal to the instantaneous value of the current flowing in the circuit. So the result of this is that you see the current flowing in load resistance R is basically equal to the instantaneous value of current in detector, right? Now, as you can see, on comparing the two cases, the signal voltage produced under these conditions has essentially the same shape, identical to the time dependence of the current produced within the detector, right? You see the two cases, they're essentially the same shape. Now you see radiation detectors are sometimes operated under these conditions when high event rates. So we use these cases when there are high event rates or timing is important. So high event rates or timing information is important, right? Then important compared to accurate energy resolution information. So this you must keep in mind. Now let me talk about the other extreme. Okay, so this is the case for large RC. So here the time constant is much greater than your charge collection time. Now you see it is generally more common to operate detectors in the opposite extreme here, where the time constant of the external circuit is much larger than the detector charge collection time. Now in this case what happens is that very little load current will flow. Here what happens is very little load current flows in load resistance R during the charge collection time, and the detector current, you see, detector current is momentarily integrated on capacitance. Now, if we assume that the time between the pulses are sufficiently large, if we assume that the time between the pulses are sufficiently large, then the capacitance will discharge through the resistance, returning, I am talking about this capacitance, right? Returning the voltage across the load resistance to 0. So, in this case, how does the signal voltage looks like? Let me show you. So here you can see this is how the pulse looks like, the capacitor discharging, you see. And here you can also compare the three cases as well. You can easily compare the hypothetical case, the small r, this case 1, and also the case 2. Okay, now you see, since this case 2 is by far the most common means of pulse type of operation for detectors, it is important, this one, it is important to draw some general conclusions. Okay, let us draw. So, some general conclusions. Now, number 1, you see, the time required for the signal pulse to reach its maximum value is determined by the charge collection time within the detector itself. Okay, now no properties of the external, you see here, there was a problem. So as I was saying, you see, the time required for the signal pulse to reach its maximum value, here you see the time required for the signal pulse to reach its maximum value is determined by the charge collection time. Understand this one, within the detector itself. Now no properties of external or load circuit can influence this rise time. So this is the pulse rise time, this one here, this is this one, this is basically the pulse rise time. Okay, now no properties of external or load circuit can influence the rise time of the pulses. On the other hand, what is this one, from maximum to downwards, this is the decay time. Okay, understand? So for the pulse here we can have a pulse rise time, this one, and the pulse decay time. So this is the decay time of pulse. Now this decay time of the pulses, or basically the time required to restore, you see, time required to restore the signal voltage to 0 is determined only by the time constant of the load circuit. This is interesting. So what I am saying is that if I have a signal pulse like this part which is the rise time, so tau rise, and this part is the decay time or fall time. Now this part is independent of the circuit features. However, this part here, the decay time, it depends, okay, it depends on the time constant of the load circuit, tau. So what conclusion can we make? So the conclusion is that the leading edge is detector dependent and the trailing edge circuit dependent. So this leading edge, this is basically detector dependent. And this one here is basically circuit dependent. This is very interesting. Okay. Now, this fact that this leading edge of the pulse, okay, is detector dependent and the trailing edge. So, trailing edge of pulse, and this one is leading edge of pulse. Okay, now this fact that the leading edge is detector dependent whereas the trailing edge is circuit dependent, this is generally true for a wide variety of radiation detectors. Now operated under the condition, this is important, where we have this condition. Okay. Fine. So we are talking about the general conclusions, and this is the first general conclusion that we have. Okay. Now let me talk about second very important feature which can be said from our discussions. Well, you see, the amplitude of the signal pulse here, what is it? It is Vmax, Q by C, right? It is determined solely by the ratio of the charge, total charge created within the detector. So what I am saying is that this amplitude here, the amplitude of the pulse here, this amplitude, so I am talking about this. So it was basically Vmax. So this is equal to Q by C, right? Now, so what I am saying is that, so this amplitude basically is determined simply by the ratio of the total charge Q created within the detector during one radiation interaction divided by the capacitance of the equivalent load circuit. But because this capacitance is normally fixed, okay, you see this capacitance, this one is normally fixed. So what can we say? So we can say that the amplitude of the signal pulse here is directly proportional to the corresponding charge generated within the detector, and is just given by the simplified expression. So we just have this thing, right? But you should remember basically that this amplitude is proportional to Q. This is important. Okay. So what can we say? Thus we can say that the output of the detector, so output of the detector operated in pulse mode here normally consists of a sequence of individual signal pulses, right? Pulses. Now each representing, this is important, each representing the result of interaction of a single quantum of radiation. Result of interaction of a single quantum of radiation within the detector. Now, a measurement of the rate at which such pulses occur will give the corresponding rate of radiation interactions within the detector. Also, we can say that the amplitude of each individual pulse reflects the amount of charge generated due to each individual interaction. Fine. Now, as you can see from this expression, this proportionality, so we will have a proportionality, Vmax being proportional to Q. But remember that this holds, as I was saying, only if the capacitance remains constant. Now, in most detectors, the inherent capacitance is set by the size and shape, and the assumption of constancy is just there. It is warranted. However, in other types, say for example semiconductor diode detectors, this capacitance can change. Okay. Now, so what I am saying is C is normally constant. However, it can change in some other detectors, say semiconductors detectors, right, with variations. Now, so what I am saying is that in semiconductor detectors, this C can change with variations in normal operating voltage. Not just voltage, you can say operating parameters. Now, in such case, the voltage pulse of different amplitude may result from event with the same charge. So, if in the detector a radiation, say 1 MeV gamma ray, I am just talking about gamma ray for the time being, it interacts and is absorbed completely. Now, and such a thing happens that the capacitance changes with variation of normal operating conditions, then what will happen is that we will observe different signal voltages, not just same, they are different, and this is a result of changing capacitance. You see? Now, but this is not what we want. Of course, we don't want this. So, in order to preserve the basic information carried by the magnitude of charge Q, this is the one, this is important, a type of preamplifier circuit known as charge sensitive configuration, charge sensitive preamplifier. We use this, and I will talk more about it in later classes. Okay, so if you insist, let me just talk a little bit about this charge sensitive preamplifier. Well, you see, what happens is that in this type of circuit, basically this charge sensitive preamplifier, it uses feedback to largely eliminate. So, in this charge sensitive preamp, what is done is basically we use feedback to largely eliminate the dependence of the output amplitude, right? This is what we wanted, the dependence of the output amplitude on value of C. And as a result, what happens is that the proportionality is restored. So this restores this proportionality. Fine. Now, but how does this configuration look like? I will show you that part later on, but you must remember that the simple RC representation which I have shown previously. Right here, the simple RC representation, it is no longer accurate, but the principle of collecting the current pulse across a capacitance that is discharged through a resistance remains valid. Remember this. Now, after these discussions, finally, let me talk about the advantages of pulse mode over current mode of detector operation. So what are the advantages? Well, of course, there are advantages. You see, that's why this pulse mode is most commonly used in applications. Now, the first advantage, you see, the sensitivity that is achieved in pulse mode is many times greater than that of the current mode. And this is because each individual of quantum of radiation can be detected as an individual pulse. So each quanta is recorded as individual pulse. This is the reason. Okay. Now, lower limits of detectability are then normally set by background radiation levels. And what happens in current mode is that the minimum detectable current may represent an average interaction rate in the detector that is in fact many times larger. Now, this is the first case, first advantage. There is another advantage which is even more important. You see, the second and even more important advantage of pulse mode over the current mode is that each pulse amplitude, you see, each pulse amplitude carries some information, and that is useful or even necessary part of a particular application. Right? This is important. A necessary part of an application. Now, what happens in current mode? You see, in this current mode, what happens? This information on individual pulse amplitude is lost, right? Is just lost, and all interactions, regardless of amplitude, they contribute to the average measured current. Now, because of this inherent advantage, these two important inherent advantage of the pulse mode, the emphasis in nuclear instrumentation is largely in pulse circuits and pulse processing techniques.